Hi, everyone. My name is Samir, and I am a research engineer at Predibase, where we have a managed platform for both training and deploying LLMs. Some exciting work we've been working on, and something exciting to talk about today is reinforcement learning for LLMs, and specifically, I'm gonna focus about reinforcement fine tuning for multi-turn agentic workflows. And yeah, we're going to refer to like RL for LLMs as RFT throughout this talk. So first, I'm going to dive into the background of RFT, what it is and how it's different from SFT, which is what I think most open source developers are more familiar with using. Next, I will discuss a very common agentic use case, which is function calling, and go through a short demo of how, with even small LLMs, we can use RFT to improve these models and make them effective function calling models with a limited amount of labeled data. And then I will discuss how these same ideas are being applied to more complex multi-turn agentic behavior in like RAG or deep research-like systems. And these are systems where the model can reason across multiple steps, gather context iteratively until it arrives at a final decision. So first, let's dive into RL for LLMs, or RFT. Now, probably the most well-known kind of RFT moment has been DeepSeek R1. And related to that are also the OpenAI O1 models. And RL really unlocked the ability for these models to do long-form reasoning and really improve performance in more difficult domains, such as math and complicated science and really complex reasoning types of problems. Now, RL has been used in LLMs for a while, right? Like RLHF is one of the most well-known algorithms used to make these models into effective chat assistants. But I think what DeepSeek R1 was able to show was a simpler way to use RL for all sorts of problems, especially enabling open source developers and those with less compute resources to start looking at ideas in reinforcement learning. Now, the main algorithm behind R10 that changed from prior reinforcement learning methods in LLMs was the GRPO algorithm. And to kind of briefly go over this, right? In the top, we have the PPO algorithm, which is what was used in most famously in RLHF. And one of the challenges of using this algorithm for, especially in the open source, is, as you can see with the two yellow trained model figures, that there's actually two models you have to be training during the process, this policy model and value model. And often the reward model itself is also another LLM. And as a result, it requires, it's very complex. It requires a lot of GPU resources to get right. And it's also a algorithm that tend to require a lot of data, a lot of human label data, preference data. Now, what DeepSeek was able to realize was that, you know, mostly what the value model is doing is telling you. So let's just take a step back quickly. The observation here, this O here, is typically going to be a prompt to, like, let's say, solving a word problem. And the purpose of the value model is to try to provide a baseline value. It tries to estimate how good do we think the model currently is at this problem, so that we can measure the actual improvement over the model's current state. And this allows the learning algorithm to work much more effectively. Now, with GRPO, they got rid of the value model, and instead they said, well, we can estimate the expected reward of our current model by actually sampling a bunch of completions from it and taking the average of those. And that is kind of like the average baseline. And we want to reward the completions, push our model towards the completions that are better than the current average of the model, right? So that's why you see here this O1 to OG, which is the group aspect in GRPO. And typically the number of completions in a group are like 8 or 16. So practically speaking, the model will be generating essentially 8 different solutions to a problem, and then we use the average advantage, the kind of average reward to over the total reward over the average to estimate which completions were the best. And so what ends up happening is the model gets rewarded more for doing well on hard questions it has a harder time getting reward on, and it gets rewarded less on easy questions where, let's say, all the completions are already getting a high score. So DeepSeek R1 focused especially on RFT for mathematical reasoning, and the reward function is very simple for that problem. You need the correct answer to the question, such as often just like a single number for a math word problem, and it checks against the model's answer against the true answer, right? And the key part is it also adds a chain of thought before doing the final answer. So if you see in the prompt here, you have the think tags, which is the model can output its chain of thought, and the answer is all that is evaluated against. Now, this is very different from SFT because we only need to evaluate the model against the answer, and the model's loss is not updated against the tokens it's outputting in the chain of thought, which let me go into why that's a huge advantage for building models that can both reason and do actions. So if you wanted to fine-tune a reasoning model for not just math, but any task you wanted, right? Like, what you would have to do is you would have to take each prompt and you would have to curate the chain of thought itself, right? As you can see in these examples. And then you're essentially training your model to learn to mimic these types of chain of thought reasoning patterns. And one downside of this is that, first of all, you have to figure out how to curate all these reasoning chains. And it tends to require a lot more data because if you just give a few examples, the model just learns to kind of memorize the patterns of thinking without learning how to think itself in a way that improves its final downstream answering ability. But meanwhile, with RFT, you really only need to have the prompts you want and the final answers. And the reasoning ability actually emerges from just the training objective itself, because if the model is able to use more thinking tokens in order to get to a better answer, then it gets a higher reward, and it will continue to do that. And the second thing is that RFT is going to learn from both positive and negative feedback. SFT, there's no real way to take an incorrect reasoning chain and answer and use that to tell the model, hey, do less of this. But with reinforcement learning, you are effectively doing that each time you take a training step. And so, you're basically able to add directly optimize what you care about. So in the example so far, you just really care about the final answer. You're able to learn from different forms of feedback and add chain of thought without curating additional tokens in your data set from what you originally started with. So now let's look at a function calling example, right? So function calling is a core agentic skill. Basically, to describe the problem succinctly, all we want the model to do in the problem I'm going to be talking about is it's going to be given a set of tools or functions, and it's going to decide which one to use, or it can use multiple of them, and what inputs need to be used for that function call. And this is very important for all sorts of like real world production use cases, using APIs, using MCP servers. One of the key problems with function calling is that even big models often get these things wrong in more chain together workflows because a failure at any step in a chain of calling tools, and if you're calling them in any sort of iterative fashion, will break down across the chain. So you need really high accuracy with each function call. So we're going to look at one function calling data set, which is this Glaive function calling data set. So on the left, we have the system prompt, and the data set has a variety of functions, from things that use calculations, like calculating a tip, or the example here is getting a news headline. So the model is told you have access to these following functions, and then what we're training and evaluating on in this demo is the model's actual, what is under that function call tag you see on the right. So the user asks, can you tell me the latest news headline for the United States? And we want the model to output this dictionary, the function name and the right arguments, right? Now, actually one of the trickiest parts about this data set, and in my experience and also using these function calling in real world problems, is oftentimes the model will try to use tools when it's not supposed to, or when it doesn't have enough information to use these tools. So one example here, which is like a real example from evaluation, is there's a tool around creating an event. And it, in the schema, it describes that all these arguments are required: the title, start time, end time. And the user says, I want to create an event in my calendar as the first message. Now, there's not enough information to actually complete this function call. And so we would want our function calling model to not call the tool, and we would want to respond to the user to actually ask for additional information. Now, what actually happens, and this is with the 32 billion parameter quiet instruct model 2.5, it's a very strong model, is it even is able to reason that it doesn't have the necessary information, but it still tries to use the tool and with just an empty list of arguments, which would be invalid. And you would have to then go through some logic of parsing this, handling this, adds a lot of complexity to the workflow. Even worse mistake, which GPT-4o makes, is we have a tool here around checking a word count. And the user asks, I have a text and I need to know how many words it contains. Now, they haven't provided the text at all, but GPT-4o puts in this placeholder text keyword as the response. And this would be actually very bad, because in a agentic workflow where everything is programmed together, we would actually get a valid response from the function of 1, and we might use that in the response to the user, making the system seem very unintelligent. Some other more common mistakes are, or I should say common, but more attributed to the model making like actual mistakes in putting together the function call, is it adds like these extra keywords, which will make it hard to parse it automatically. Or in this case, with this long function call, it actually gets the syntax wrong and it has an extra right brace, right? So instead, we can use RFT to train a model to select the right function calls and inputs. So we're going to have 2 reward functions, one around correct tool use and one around formatting. So the formatting one is fairly simple. It's mostly just to make sure that the prompt or the completion has the right structure where it's easy to parse and exactly extract what we want. So check if the thing tags are present, and then that they come before the tool tags. There's only one set of these think and tool tags, or you can change that constraint if you have multi-tool calling. And does the tool itself follow a valid syntax? Is it basically parsable as a dictionary and has a name and arguments field? And one cool thing you can do is also assign partial rewards in your reward functions, which help guide your model if it's getting in the right direction, right? Which can significantly help the learning process. Next is the correctness function, and this one is fairly simple, right? If the ground truth doesn't use the tool and the model also says no tool to be used, then it gets a full score of 1. And then in the case where both use a tool, get partial credit if that decision is correct, and then additional credit for if the tool names match and if the arguments match. Now, the results are pretty striking, right? So on the left here, so first of all, this evaluated 150 holdout examples. And for the RFT, we're only using 20 labeled examples. So on the left, most one with the 83 correctness score with that same reward function I showed you. A Quen 2.5, 32 billion. These are all instruct models. Gets 83 out of the gate, 0 shot, which is like pretty good, right? A lot of the mistakes to make are the kind of mistakes I showed you, which are, in my opinion, more around like reliability. And the 3 billion model, 10 times smaller, gets 60, score of 60. And if we train it on 20 examples with SFT, right, we just train it directly on those labeled examples. It goes up to 72. And if you go up to all the way to 2,000 examples, it still only goes to 79. Like you quickly start hitting saturating returns. It's unclear how much data you'd really need to get to that kind of 90, 95% threshold we really want. But with reinforcement learning, it's able to get 99% correctness on just 20 labeled examples. And a lot of this is because the model is actually doing a lot of exploration and learning beyond just the examples, and it generates so many different completions. So to kind of show you more of the behind the scenes, I'm able to train and look at these models using our platform on Predibase. And one nice thing is you can see, first of all, these are the reward functions, right? Like they're very simple Python functions. Anyone can really write these. And this is all you really need to define to do this sort of reinforcement fine tuning. The format function, and one function I'll come back to, is a length penalty, which is basically I reward the model for shorter overall completions with the goal of, hey, can it compress its reasoning chain as it starts getting better at the task? So look at the reward graphs, right? The model starts around that 60% mark and actually very quickly able to get a very high correctness reward over time. This also applies to the format and the total reward. And as it starts getting better and better correctness over here, it starts also doing better on this length reward, which means length reward going up means the length of the output is going down. And to look at some completions to really understand what these models are outputting, right? So we can see epoch 1, right? The question here is basically the model has access to a translation tool, and the user is saying, I have this sentence that I want translated. Epoch 1, the model so in this epoch, there's eight different completions. So if you recall the GRPO algorithm I was talking about, for this one prompt, the model spits out 8 different completions, and the rewards are aggregated across those to compute the loss function. So you see this one is clearly very wrong. It doesn't even use the tool at all, and it just has this placeholder. Some of them it does better. This one I got a correctness of 1, but fairly mixed results. But as we get farther into training, almost every completion has a correctness of 1, right? Some of them don't, and then this length penalty also tends to be, this length reward starts to go up, and you can see the chain of thought right here. It's fairly long, but if I go to a completion like this, the model has a very small reasoning chain. It's able to compress it and still get, like for example, this one, it gets it right here. So this is one of the highest scoring completions here, where it has a nice and compressed chain of thought and accurately uses the tool. So now I want to talk a bit about how these ideas can apply to multi-turn function callers, systems like deep research or other things you can think about browsing. So one approach, right, which I think can work a lot for situations where the actual tools you need to use or the workflows are not extremely complicated, but they're broad and diverse, is doing the same sort of approach I showed, using targeted data to train specialized small models for doing these actions, and having a general purpose orchestrator model to organize them, right? And what's nice about this is you can build in a more modular fashion. You can curate more subsets of data for each subproblem you have, and you can take advantage of the speed of these small models to make this kind of system, which dispatches a lot of LLM requests, much more efficient for a production workflow, right? But there's also a lot of work being done in, this is already covered. A lot of work being done in end-to-end agents using reinforcement learning. So really the idea behind this is not so different from what I've shown you so far. You have this thinking, you have then the model making an action, but then you have a loop where you get an observation from that action. And the model can then continue to think and act. And so this is very similar to taking the React style prompting and just applying a training objective to it, right? And this can help you model more complex interactions with the environment and requires more long context learning. So one recent paper that has applied this workflow to improving RAG is this research paper, right? So you can see that on the top, it has essentially the same GRPO algorithm, but there's a loop between the LLM policy and search itself. And how this practically works is the model will continue to generate tokens, and on the back end, you're just reading the model's token outputs. But when you see this search tag, right, you can interrupt the model completion. The system goes and it actually does the search, it returns the results, it appends it to the messages so far, and the model continues. And actually nothing changes about the training objective when you end up doing this. The only difference is that the observation tokens, so in this case, the search results, are not computed as part of the loss because the model has not generated them, of course. So yeah, and the reward function they use for this task is using just the F1 score. So they take the true answer, right? Like here, the president of the United States was founded was, they take this value inside that slash box, James Madison, and they compare it against the true one, which in this case would also be James Madison. And they just check the word level F1 score, a basic syntactic similarity score. And even with this approach, right, they're able to do significantly better than other standard RAG approaches using both 7 billion model and a 32 billion Quen model. So just an example of the sort of pattern the model has during training. You can see it can think, search, get results, continue this in a loop until it decides to output these answer tags, and that's when the episode is terminated. A similar and more kind of advanced problem is this deep researcher work where they do the exact same sort of thing, but not only do they have a search engine, but also a browsing agent that can navigate the web when coming up with answers. So just to kind of summarize and go through the conclusions, right? RFT is exciting because it can enable reasoning, tool use, and interactions with an environment in a loop without forcing you to explicitly curate, this is how you use the tool, this is the search query, these are the chain of thoughts. You only have to reward the final answer you care about. And for coding, this could be passing unit tests. For QA, this can be a particular string, or you can use an embedding similarity. You can use LLM as a judge. You can be very creative with how you assign the reward, right? It enables model exploration, which is really what SFT lacks and why it's much more data hungry, because you have to essentially curate that exploration in the data itself. And small models can also use RFT for doing things like function calling, doing things like we saw, like advanced RAG workflows with the 7 billion model and RE search. So that concludes my talk. Now we have time for some questions. Sorry, I'm trying to figure out what this question section is. Yeah, so let me explain that more, right? So like, I think actually the looking at an example is really useful. That's what really drove some of this home for me personally. Right, like, let's go back to this example, right? So say I tried to solve this problem. I had this question, this user message, and I already knew the answer as well, right? The answer is effectively this tool call. Now with SFT, what would I do? I would basically have this example, and I would say the model is trained to predict these tokens, right? Um, the model is essentially then just learning to kind of imitate some outputs. But with RFT, what's happening here is this is just one training step. In this one training step, the model generates this completion. It does all this reasoning and it does this. It also generates this completion, which it got right. It generates this completion, which it got wrong. It generates these 8 different completions in one training step. And you can imagine, right? It's kind of like if you went and tried something 8 different times and you said, oh, the times I did this, I got a score of 1. The times I did this, I got a score of 0.5. The times I did this, I got a score of 0. And through that process is essentially exploring the space of completions and also reasoning in order to get to the right answer. Yeah, so for RFT, definitely the most informative metrics are basically the rewards. But yeah, I think like you want to just have some holdout evaluation to kind of check the rewards against overfitting. It's not too different from like other machine learning things like that, but there can also be unintuitive trends in the reward. I've seen things where the reward is not going up for a while and then suddenly goes up. So not like a clear answer on that, right? Like I think reinforcement learning for this type of stuff with LLMs is still fairly new. So there are also like things you can look at, like the standard deviation of the reward, like how much variance is there, and a lot of work is around kind of stabilizing these training objectives. How many epochs do you typically use? I would say it typically uses more epochs, but it's also very dependent on how much data you have, right? But typically training for a while can help a lot because of kind of the exploration thing I talked about. It takes a lot for the model to start like memorizing the data fully because it finds different ways to get to the same answer, and that helps with its robustness. And then Sarisha asked, so yeah, for reward models, right, it's hard to do human evaluation because it's going to slow down your training a lot. You need someone to go like evaluate the thing. But I think using user feedback in some ways is a very interesting problem people are trying to think about. And with an automated reward model, you don't need to terminate the loop. Basically, the generator, the policy model is deciding when to stop generating. And typically, there'll be some sort of like people will have some sort of threshold after which they'll say, all right, the model has to stop and it gets a reward of 0 because it like thought too long or something. That's more of a hyperparameter. And the reward model only judges the final output after the generation is done. So SFT is just next token loss prediction, like exactly what the pre-training objective is, or instruction tuning, sometimes where you don't include the prompt in the loss. So the model is just learning to predict the next token given the text you've given it. So the thing is, ChatGPT is not capable of doing this in terms of doing reinforcement fine tuning for you, right? Like you have to use a platform like ours or like an open source library like TRL or VRL, especially if you want to like model any sort of environment you want to build. There's no way to upload an environment to ChatGPT and say, oh, train an RL model on this. And on top of that, it would probably be quite expensive to do that. Yeah, I think that's all the questions I saw. Well, thank you for listening, everyone. Have a great rest of your day. looking forward to the rest of the presentations as well today.